Hi everyone, this is a very quick tutorial on how to use our Python package for estimating uncertainty in paleomagnetic direction, specifically at the specimen level. So where you have a collection of specimens that have been analysed using PCA, you've got the characteristic remnant magnetization, you've got an MAD and so on, and you want to find out an average direction and the uncertainty on that average direction. Now, if you're watching this video, you've already found your way to the page that describes the software. The easiest way to run the software, if you only have a small amount of data, is actually using Binder, which is a free cloud service that we can launch, interact with, get the results, and so on. Alternatively, if you've got a large amount of data to process, then you may want to install the package locally on your system, in which case feel free to send me an email on my ANU email address and I'll be able to provide advice on how to do that. You can also find all the package code and an interactive Jupyter notebook by following the link here. That's all on GitHub. But today's demonstration is how to use the system on Binder. So to launch the Binder, launch the workbook on the cloud, we simply click the Binder link here. That will take us to Binder and that will start a new instance of the interactive Jupyter notebook on the cloud. It takes a little bit of time to start. If you want to see progress, you can simply click on the show button here, but I think it's probably almost done because it's a relatively small package. We see some cogs and it will open up the interactive Jupyter notebook. Now, it doesn't matter if you're not familiar with Python or Jupyter. It's programmed as a graphical user interface, so it's simply a case of inputting your data and pushing a button. So as I said in the introduction, this is for specimen directional uncertainty. So if you've got a collection of PCA-based characteristic remnant directions, then you can estimate the mean direction and its uncertainty. So here is the information on the input parameters and the box where we can actually input that information. So we've got PCA estimated directions, and here's the box where we can enter them. We're going to put one direction per row in the box. It consists of a declination in degrees, inclination in degrees. N is the number of demagnetization points you use to define your PCA. MAD, the maximum angular deviation from the PCA, again in degrees, and then did you use an anchored fit in the PCA or not? Now, at the moment the input table only has one row. We can add rows simply by clicking add row, or you can remove rows using the remove row button. And to keep this simple, I'm only going to imagine that we've got 3 different specimens that we're interested in. So I've input 3 rows. You can see that the values are effectively empty at the moment, and we can just start defining our data. Now I'm just going to make some data up for simplicity, so I'm going to say my first sample I had a declination of 45 degrees. I had, for example, an inclination of 27 degrees. Maybe the number of demagnetization points on that specimen was 4. I had an MAD of 2.1 degrees, and was that fit anchored? Well, if it was, you can just click the checkbox here and that will say that you used an anchored PCA in that estimate for that specimen. Now let's put in this information for specimen 2. So again, a declination maybe 42 degrees, inclination 28 degrees, and maybe I've got a lot of data points defining this PCA, so maybe I've got 8. MAD, maybe that was 4. Was it anchored? Well, we could say no, this one wasn't anchored, so when we look at this tick box we can just leave that unticked. Last specimen, maybe a declination of 40 degrees, inclination of 25 degrees, and maybe again I have 5 data points on my PCA analysis there, an MAD of let's say 5.2 degrees, and we could say this one was anchored as well. So once all that information's input, you can simply scroll down and say process data. And the result should come very quickly. What we've got on the left hand side is the mean direction and its alpha 95 incorporating the uncertainty using the method outlined in our paper. And this is the traditional estimate of the mean where uncertainty propagation isn't included. So that's where we just take each of these characteristic remnant magnetizations to be a unit vector direction. So these parameters are not saved anywhere, you would simply need to write them down. So again, if you want to process a large amount of data, I'd actually recommend that you install the software locally and run it. Now, if you've made a mistake, you can actually just go back and simply change the numbers in this table. So suddenly you might think, oh, whoops, that last sample, I put it in as anchored, but it wasn't. So now you can just uncheck that box, for example, and click the process data again. Now, it won't remove your initial result, but what it will do is just add a new result down at the bottom that's been revised for the change that you made in the data box. Okay. Now, once you're finished, you can simply close the tab. That will break your link to the cloud. Nothing is saved on the cloud. So again, once you process your data, it's important that you record the results because they won't be saved anywhere. Okay. If you're working through a large amount of data and you leave your session inactive, for example, for about 5 minutes or so, then your link with the cloud will also be broken as well. So I'd suggest that when you start processing data, you're actually ready to start putting in all your numbers and get the result. If you've got any questions about the binder version of the software or installing the software locally, or you've got a bug report or questions concerning how the technique works, then of course feel free to email me using my ANU email address. And that's the end of this tutorial.